There we go.
So hello everyone, I'm Mathilde Marchandon. I'm a postdoc at LMU Munich. I'm working with Alice Gabriel and I'm also involved in Rachel and Daniel PhDs. I'm kind of new in dynamic earthquake simulations. I did my PhD in earthquake geodesy, and it's been, I think, 2 years and a half that I'm working now with dynamic rupture simulations, in particular to try to better understand what the observation we made with geodetic data. So today I will give a lecture about dynamic rupture simulations. So I'll start with an introduction to dynamic rupture simulation. Then I'll go over the key modeling ingredients that need to be prescribed when we perform a dynamic rupture model. And we will see how these initial conditions are constrained or not very well constrained. And finally, we will look at some examples of dynamic rupture simulation to illustrate how these kind of models can improve our understanding of earthquake rupture. So dynamic rupture simulation are physics-based simulations that couple fracture mechanics to seismic wave propagation to simulate the spontaneous propagation of an earthquake rupture. So from its nucleation to its arrest. So on the right, you can see the result of a dynamic rupture simulation of the Canamaras earthquake doublet with the slip rate on the fault and the simulated waves at the surface, in the volume. So in this kind of models, the outcome of the simulation is not predetermined, but evolve as a consequence of the model's initial condition and the way the fault yields and slides, so which is controlled by the friction law. So dynamic rupture modeling is different from, for example, kinematic or static fault slip modeling. So in kinematic or static model, we look for the distributions of slip that best reproduce seismic or geodetic observation. While in dynamic rupture simulation, as I said, we prescribe the initial stress, the fault strength, and the rupture spontaneously propagates or not, depending on the initial condition. So in dynamic rupture model, the earthquake rupture is idealized as a spontaneously propagating shear crack on a frictional interface in an elastic solid. So here on the right, you have a schematic representation of the problem. So we solve for the elastodynamic equation for motion everywhere in the volume, coupling with additional equation governing frictional sliding on a boundary interface representing the fault surface. So basically, during the simulation, at each time step, we solve for the elastodynamic equation to update the velocity and the stress tensor. On the faults, we evaluate if the shear stress is larger than the fault strength. And if it is the case, then we compute the slip rate using the friction law. Sorry. And then we apply the slip rate as a boundary condition in the elastodynamic equation, and we update the stress everywhere, and also if needed, the friction parameters. So we don't have an analytical solution for dynamic rupture simulation problem, so we need numerical techniques. So there is a lot of different dynamic ruptures code, such as different numerical techniques. So as you can see here, you have a list of the principal codes in dynamic rupture simulation. The good thing is that spontaneous, these codes are verified by spontaneous rupture code verification project, which is a set of benchmark exercises to check that the dynamic rupture simulation code work as they should. So many of them are 3D codes, so we can include all kinds of complexities, such as topography, 3D medium properties, heterogeneous conditions on the faults, and of course, because there are 3D, those dynamic rupture simulations are computationally very demanding. and therefore requires high performance computing facilities. So what are dynamic rupture models used for? So dynamic rupture models are used in three main types of study. So either we use them to study a specific earthquake, for example, to understand the initial conditions that allow reproducing a particular rupture behavior that was observed during a real earthquake. Or we can use dynamic rupture model to perform a parametric study. So in this kind of study, a suite of scenarios are used to analyze the impact of a given set of parameters on the rupture dynamics. So here, for example, on the figure, this figure shows the rupture style as a function of the seismic ratio and the nucleation size. So they show that depending on these two parameters, the rupture can be crack-like or pulse-like or subshear or supershear. Or you can also use dynamic rupture simulation to infer realistic and physics-based earthquake scenarios for a given fault system. So here, for example, you have dynamic rupture scenarios for the Anatolian fault, so the segment that is located in the Sea of Marmara. It's from Aoshi and Uric. And currently there is a lot of work going on toward using the synthetic ground motion produced by these kind of scenarios to inform probabilistic seismic hazard assessments. So later, I'll show you some examples of study illustrating the three categories. So now let's look a little bit more in details in the input parameters that we need to prescribe. So we need to prescribe the initial stress, the fault geometry. We need also to prescribe the rheology of the medium. We need to choose a friction law that will define how the fault friction evolve with slip during the rupture. Yeah, and then the output are the rupture dynamics on the fault. So we have the stress variation, the evolution of friction, and all the kinematic parameters that are derived from dynamic parameters. So the slip rates, the slip, yeah. And we can also output any kind of synthetic data, so seismic data or geodetic data that we can compare with real observation. So let's start by how do we constrain the initial stress. So it's a very important parameter because it will determine the stress drop and therefore the size of the simulated earthquake. And it's not very well constrained, so there is many strategies to constrain the initial stress distribution. So first, we can use the Andersonian theory of faulting to, can I move this? To constrain the initial stress. So Andersonian stress regime, it means that one principal stress is vertical, and depending on which one is vertical, we have either a normal fault regime or a strike slip regime or a truss fault regime. So to define completely an Andersonian stress regime, we need to know the orientation of the maximum compressive stress, SH max, and we need also to know the stress shape ratio, which controls the relative amplitude of the principal stress components. So this can be constrained from observations. So once we have our stress regime that is fully oriented, we can compute the full stress tensor. And if we have geometry with a non-planar geometry within an homogeneous Andersonian stress regime, then we end up with homogeneous initial stress on the faults. And then we set the slip vibratoric stress amplitude to get the right size of earthquake that we want to simulate. Another way to constrain initial stress is to use a static slip model. So when we want to model given earthquake. So we can use a static or a kinematic model, and we can use it to compute the stress change associated to this model. And then we can use the stress change to constrain the initial condition. So we can either add the stress change on top of the residual strength to have a variable initial stress, or we can alternatively use this stress change to have variable residual strength, but a constant initial stress. We can also constrain initial shear stress from geodetic coupling model. So a coupling model tells you which part of the fault accumulates stress and in which parts the stress are continuously released by fault creep. So we can use this coupling model to estimate the slip deficit rate on the faults, and then you compute the shear stress change associated with the slip deficit rate, and again use it to infer the initial condition to compute the initial stress. So for example, here it's done for simulate scenario of earthquake in a subduction zone in Japan. Another way to constrain the initial stress is to use the stochastic shear stress distribution. So, for example, like here in Gatteri et al. So generally we used this kind of method to produce higher frequency in the ground motion when we are interested in simulated realistic ground motion. And another method that we can use is to use initial stress constrained by a geodynamic model. So this is an example from a paper from Anthony Jourdan and collaborator. It's not published yet, I believe. And this is used to overcome the limitation in observational constraints. So because we don't really know the state of stress in the stress, so we can use a long-term geodynamic model to constrain them. So now another very important ingredient in dynamic rupture simulation are the fault friction. So the friction law describes how the fault strength involved with the slip or with the slip rate during the rupture. So the most common used friction laws are the linear slip weakening and velocity weakening friction law. So in the slip frictioning law, the fault friction only depends on the slip, and it's characterized by the slip weakening critical distance d sub c. So the fault starts to slip when the initial stress reaches the fault strength, and then the fault strength evolves linearly from a static level to a dynamic level over a critical slip distance dc. So it's a very simple friction law. There is not many parameters to prescribe. This kind of friction law favors crack-like ruptures. So it means that the fault continues to slip relatively far behind the rupture front. It's because with this friction law, the fault is not able to heal. And yeah, but we can still generate pulse-like rupture if there is heterogeneity in the, for example, in the initial stress or in the fault geometry. In the velocity weakening friction law, so the fault friction is inversely proportional to the slip rates. So in this law, the relative difference between A and B parameters control when the fault is velocity weakening or velocity strengthening. So when A minus B is negative, the fault is velocity weakening, meaning that the friction decreases as slip velocity increases. So the larger the slip rate, the easier it is for the rupture to propagate. On the contrary, when A minus B is positive, then the friction increases as slip velocity increases. So if the rupture, for example, enter a velocity strengthening area, then it will be hard for the rupture to propagate, and at some point the rupture will stop. And there is also, of course, a much more complex friction law. Then we also need to prescribe the medium properties. So in many simulations, the medium is purely elastic, with the elastic properties computed from a 1D or 3D velocity model. We can also add any kind of complexity in the medium properties. So for example, we can add a low velocity zone around the faults because it's something that we observed in real life. So here on this figure, you have a figure showing how we can, it's just an illustration, but the 3D community velocity model of California is embedded in a dynamic rupture simulation for the Ridgecrest earthquake. And we can also use more complex rheology. So for example, we can use elastoplastic rheology, in which the off-fault medium can deform also plastically. So for example, we can use Drucker-Prager off-fault plasticity, where you can have plastic deformations that accumulates when the stresses locally exceed the plastic yield strength. The plastic yield strength of the rock that depends, among other things, on the plastic cohesion of the rocks. So for example, here on this figure, you can see cross-section showing the distribution of plastic damage for a strike slip simulation that resemble the flower-like structures that are inferred from seismic and geological data. So let's move to the third part of the lecture, where we will look at some examples to illustrate how these kind of models can improve our understanding of earthquakes. So let's start with parametric studies. So as I said, with this kind of studies, we test how a given set of input parameters can impact the key aspect of the rupture. So there is a big, large body of literature with parametric study that evaluates the impact of all the input parameter to the rupture characteristic. So just for an example, so for example, we can use this kind of study to evaluate the conditions that govern supershear rupture transition. So supershear rupture is when the rupture propagates at speeds higher than the shear wave velocity. And it's important to understand under which condition a supershear rupture can form, because this kind of rupture induces larger ground velocity and acceleration further away from the fault compared to subshear rupture. So here on the left, you have a figure from Dunham where he used dynamic rupture simulation in an homogeneous media to show that the seismic ratio is this parameter here. It's a measure of the initial loading stress relatively to the peak and residual strength. So this figure shows how the seismic ratio must be smaller than some critical value for the transition to occur in an homogeneous media. And here you can see a figure from Wang and collaborator that shows that when there is a low velocity zone around the fault, as it can happen, for example, for mature faults, then supershear ruptures can occur under relatively low fault stress compared to homogeneous media. So now I will illustrate how dynamic rupture simulation can be used to explain a particular feature or some rupture characteristic of a specific earthquake. So I'll show you first the result of two studies I have been part of that focus on the Karaman-Maras earthquake doublet. And I will also briefly touch upon dynamic source inversion, which is a data-driven method used to infer the pre-stress level and the fault friction parameters based on physics-based simulation. The Karaman-Maras Turkey earthquake doublet, so I'm sure everyone knows very well this doublet. So it's composed of two very large earthquakes. The first event nucleated on a splay fault. Here, this small fault, and then propagated bilaterally on the Eastern Anatolian faults. And 9 hours later, a magnitude 7.7 earthquake broke the 150 kilometer long Savon Kardak fault. which is located 90 kilometers north of the first epicenter. And it was a really unexpected sequence during which we observed really unusual behavior. So the first unusual behavior that we observed during this sequence is backward branching during the first events. So as I said, the earthquake nucleate on this small splay fault here, and then propagate on the east Anatolian fault. And what it is unusual is that the rupture did what we call a backward branching. The rupture goes back in the other direction. And in simple dynamic rupture model that look at branching fault, this kind of fault branching is highly unfavorable from a dynamic perspective. Another unusual observation or surprising observation that we observe for this earthquake is that the second event, so we have a big deviation of the rupture path for the second event. So it nucleated here, and instead of propagating straight on this fault that is mapped here as an active fault, the earthquake turned and propagated in another direction. So in this study, we used dynamic rupture simulation to try to provide physics-based explanation to this observation. So about the initial condition of the simulation, the fault geometry that we used follows the surface fault rupture mapped after the earthquake from geodetic data, so from Sentinel-2 optical data. We assume an Andersonian stress regime for track slip faulting. So we constrain the orientation of SH max from stress inversion and a few trial and error simulations. So here on the figure, in blue, you can see the SH max and SH mean used in our simulation. We use a relatively constant pre-stress level within the medium, except along the central segment of the second event to better match the magnitude of the earthquake. And we use a slip weakening friction law with very basic parameters value. And we simulated both events in a joint simulation, such as the second event accounts for the stress changes of the first event. So we do not explain the 9 hours between both events. It's just that we parameter the second nucleation to happen after the end of the first rupture. So here at the bottom, what you can see is the pre-stress level on the model faults. So yeah. So here you can see the slip rate during the simulation. So let you have a look. So the earthquake nucleated on these splay faults, and then it starts first to propagating northward, and then after a small delay, the rupture starts to propagate in the south parts. So you can see this on this figure also. So first the earthquake nucleated here, then reach the fault intersection, start to rupture in the northern direction, and then after some delay, start to rupture in the south direction. So in fact, what the dynamic rupture simulation model show is that it wasn't a backward branching that occurred during the earthquake, but only an apparent backward branching. What happens is that first we had a forward branching from the splay fault to the northern part of the East Anatolian fault, and then the propagating rupture on the northern eastern Atlantic fault, increase the stress on the southern part, and so the rupture start to propagate bilaterally. So it's just not a backward branching. Another thing that our model reproduces well is the absence of instantaneous triggering of the magnitude 7.7 faults during the first events. So here what you see is stress changes produced by the first event on the fault of the second event. So here you can see the peak dynamic Coulomb stress changes due to the passing seismic waves. And you can see that the shear stress during the first event stay well below the fault strength. And here you can look at the static Coulomb stress change. The stress change due to the static slip. In red is when the fault is closer to failure, and in blue it's when the fault is further away from failure. And you can see that the second earthquake nucleated here, and so this area has been brought closer to failure by the first event, but really not much, just a tiny little bit. And this part of the fault that also ruptured during the simulation undergo a very larger negative dynamic stress change. So I think from this we can say that the first event didn't trigger the second one, but it only modulates the dynamic of the second event. So here it's the rupture dynamics of the second event, and see here, so it's a simpler rupture compared to the first event. The rupture simply propagate bilaterally before dying. And we have some superficial rupture on the west part of the fault for the second event that has been also inferred from observation, from data-driven method. Oh yeah, and we also explore why the second event didn't break these faults here that are connecting the so this fault with the East Anatolian fault. So we simply rebuild a mesh adding these faults that connect the two fault system, and we rerun the simulation using the same initial condition. And what we found is that this segment is in fact simply unfavorably oriented with respect to the regional stress field. So you can see that here, looking at the pre-stress level on the faults, the stress orientation in our model, and just a very low pre-stress level on this fault. And so the ruptures, when it reaches this intersection, propagate on the other segment because it's simply the initial stress is simply higher on this part of the fault. We also compare our synthetic data and our simulation with data-driven methods. So here we compare the slip rate and the slip during the rupture with a kinematic model. And what is quite impressive is that both the kinematic model and the dynamic model are very similar, both for the first event and the second event. We also compare our synthetic with geodetic data. So here you have the east-west and north-south displacements measured from optical correlation. And here you have the simulated horizontal displacement, and you can see that it's quite similar. So we are not doing an inversion, but we are able to reproduce quite well the surface data with rather simple initial condition. And here, what you can see is fault offset along the East Anatolian fault and along the second event faults. And the fault offset, so the slip at the surface in the fault is quite well reproduced by the model. And what was interesting is that the fault offset variation is very well reproduced. So the fault offset variation that is due to the fault segmentation. And finally, we also compare with the grand motion, and you probably already know quite well these figures thanks to Rachel. With our simulation, we capture the amplitude and the timing of the waveform and quite well, in particular for the first event, not that much for the second event. And that's it for the Turkey doublets. And now I would like to briefly talk about dynamic source inversion. So, as I said at the beginning, dynamic rupture simulation are not like static and kinematic inversion, but now we can use also physics-based simulation in inversion. So the principle is that we estimate the spatial distribution of initial stress and frictional parameters on the faults from seismic data. So, for example, there is Galovic and collaborators that developed Bayesian dynamic inversion. So what we had put is an ensemble of models that allow to estimate uncertainties. So the principle is that we prescribe the fault geometry, the normal stress, the velocity profile, and we look for the pre-stress levels, so the initial stress and the friction parameter that best explain the data. So it's very, very expensive, and to do that, we need to run several millions of forward simulations to end up with a preferred model and with uncertainties. So here it's an example of this dynamic inversion method used for applied to the Parkfield earthquake. So what you can see on the figure, it's a seismic dynamic rupture parameters. So the stress drop, the peak slip rate, the co-seismic slip, the rupture speed, the rise time. And here you have the fit of the dynamic rupture inversion synthetics to the data, so to the GPS and the ground motion data. And what is interesting is that even for such a moderate earthquake, can see that the results show a lot of heterogeneities, and we have a lot of variation in the dynamic and kinematic parameters. So now briefly the last part. Now I would like to illustrate how we can use dynamic rupture simulation to forecast realistic scenario for a given fault system. So I'll show you the result of a study that I lead with, which is about forecasting earthquake scenarios for low angle normal faults. So why we want to do that? Because the Anderson and Thoria faulting predicts that in an extensional tectonic regime, that is when the maximum compressive stress is vertical, normal fault should form with an angle of 60 degrees with respect to the Earth's surface. And the theory also predicts that to reactivate a pre-existing fault as a normal fault, the tip angle should be comprised between roughly 40 and 80 degrees. And the theory is consistent with what we observe in the seismic record, because if we look at the global compilation of large normal earthquake of magnitude larger than 5.5, with unambiguously discriminated rupture planes, we can see that those earthquakes occur on fault dipping between 30 and 70 degrees. And yet, we have low angle normal faults worldwide. So, for example, we have the Papua New Guinea low angle normal faults, for which all paleoseismological records suggest that these faults host infrequent but regular magnitude 7 earthquakes. We have also a low angle normal fault in the Gulf of Corinth in Greece that you can see here, delineated by the microseismicity. And another example is the Alto Tiberina fault in Italy. So we can clearly see here the microseismicity and the low angle normal faults. So the goal of this study is to use 3D dynamic rupture simulations to try to estimate under which condition low angle normal fault can produce or not large earthquakes. So we try the 3D dynamic rupture simulation. And we apply this work to the Alto Tiberina fault in Italy. So the Alto Tiberina fault, it's a fault located in the Northern Apennines. So here the thick gray lines is the surface fault trace, and the thin gray lines are the isodepth contour for the fault. So the fault is dipping in towards the northeast. It's a very large fault that if the entire fault breaks, it could host a magnitude 7 earthquake. So as we saw just before, this fault is seismically active. We also know from GPS data that it accommodates a large part of the extension in the Apennines. And we also know from a coupling model that a part of it is creeping. And finally, there is some frictional experiments that have been made on fault rocks on the Zukole fault, which is the exhumed analog of the Alto Tiberina faults. So frictional experiment on this fault suggests that it's a weak fault with a very low static coefficient of friction. So in our model, we include all the faults in the area for which we can constrain the geometry. So we have two main faults for which the geometry is known from seismic reflection profiles, the Alto Tiberina fault and the Gubbio fault here, which is a small antithetic fault to the Alto Tiberina fault. We also include 4 secondary segments in the simulation on which moderate earthquakes, so moderate I mean magnitude 3 earthquakes have occurred in previous years, and for which the geometry is constrained from seismicity, because we have a very precise earthquake catalog in the area thanks to the Taboo near fault observatory. So we use a slip weakening friction law. So as you now know, the faults start to slip when the initial stress reaches the fault strength, and then the fault strength evolves from a static level to a dynamic level over a critical slip distance DC. And we use a very low static friction on the ATF, motivated by the rock experiments made on the Zukale faults. And we use a classical 0.6 coefficient of static coefficient of friction for the other faults in the system. So we did several tests. We first tested an Anderson normal footing regime. And we also infer some other simulation using the coupling model for the Alto Tiberina fault. So I considered an Andersonian normal faulting regime with SHMX oriented 160 degrees, which is the average in the Alto Tiberina area. The pre-stress level and the model faults, so the pre-stress level R is controlled by the pre-stress level R0, which is the pre-stress level on an optimally oriented fault. So an optimally oriented fault in the regime that we consider, it's a 60-degree normal fault. So the pre-stress level tells you how close from the rupture you are. So if R equal to 1, it means that you are critically stressed. And on the contrary, if R is close to 0, it means that you are very far from rupture. So in all our simulation using Anderson and stress, the amplitude of the initial stress are controlled by these R0 parameters. So R0 parameters, again, is a pre-stress level of an optimally oriented fault within the stress regime that we consider. And then this stress regime for this optimally oriented fault is projected on the model fault. And so we have some distribution of shear stress and normal stress on the model faults. So we investigate the impact of different parameters on the result of the simulation. So we first look at how the fault geometry impacts the result. So how a planar fault versus a 3D fault, so fault with some topography on it, impacts the results. We look at the impact of the pre-stress level, the static coefficient of friction, and the nucleation location. So here, what I show you is the result of a simulation that uses planar faults that is 70-degree dipping as the Alto Tiberina fault. And what you can see is that the ruptures fail to propagate because so we use a pre-stress level for an optimally oriented fault of 0.7, but because this fault is so badly oriented in the stress fields that we consider, it leads to a pre-stress level on the fault of only 0.2, and so there is not enough pre-stress to propagate the rupture. Now, if we use the complex fault geometry, the non-planar fault geometry that is constrained from data, seismic profiles data, we can see now that the pre-stress level on the fault is very heterogeneous, which with some part of the fault where the air ratio is quite high, above 0.7, and some other part of the faults where the stress ratio is very low. And so this heterogeneous distribution of the pre-stress level is due to the local deep angle of the fault, which is variable on this model. And so when the fault is very shallowly dipping, the pre-stress level is very low. And on the contrary, in the area where the local deep angle is steeper, then the pre-stress level is higher. And so now if we nucleate the simulation in this area here, we end up with very large earthquakes that breaks the entire fault. So here it's a magnitude 7.3 earthquake. So here we just test the impact of the pre-stress level. So the higher the pre-stress level, the lower the earthquake. Here I test the impact of the static coefficient of friction, so the fault strength, the static fault strength, and without surprise, the higher is the static friction, the lower is the rupture, and if I use a static coefficient of friction higher than 0.45, then the rupture does not propagate. I also tested the impact of the nucleation location. So here on this figure, you can see the different locations that I have tested. And among all these tests, only 2 nucleation locations lead to a large earthquake, while the other one, the ruptures that just don't propagate. And to finish, now I will show you a model that is constrained by the interseismic coupling model for the ATF, for the Alto Tiberina fault, which has been constrained from GPS data. So to constrain the initial condition of this simulation, we compute the slip deficit rate. So to do that, we multiply the coupling coefficients by the long-term slip rate for the ITF. And from these sleep deficit rate, we compute the associated shear stress change that we used to compute the initial stress. So here is the result of such a simulation. So here you have again the pre-stress levels that show you how close from the rupture the fault is. And when I nucleate a simulation in the most stressed area, we got a 6.7 earthquake that stay in these patches of high stress. It doesn't propagate further up deep on the fault. So just quickly, we conclude that large earthquake can occur on a low angle normal fault under purely Andersonian extensional stress, as long as the nucleation is located in the beta-oriented part of the fault. So because the fault is not planar, even in this low angle normal fault, we can produce a large earthquake. And we also saw that taking into account the coupling model, the simulation is confined in the locked part of the Alto Tiberina fault, which limits the earthquake magnitude. So that's it for today. So just a very brief summary. So dynamic rupture simulation are physics-based simulation that couple fracture mechanics to seismic wave propagation to simulate the rupture, an earthquake rupture from the propagation to its arrest. And I hope you are convinced that it's a very powerful tool that can be applied in various ways to gain insights in the rupture process.
Thank you, Mathilde. Congratulations for a very interesting presentation. So
Thank
you. You explained a lot, and okay, I have many questions, but I guess it's better to have the students asking their own questions. Please feel free to raise a hand. Daniel, yes.
Yes, thank you. If you don't do the source inversion modeling with all the models you run that are very expensive computationally, how do you get your error in the end? If you
we do it. Sorry, I didn't explain very well this part. So where it is. I am still sharing my screen? No.
Yes, you are.
Yes, okay. So can you repeat the question?
Yeah, so you said for the source inversion part, you run a lot of models, right?
Yeah.
To have the best model stand out in the end. And
so you run a lot of several millions of forward simulations, and for each simulation you change the distribution of pre-stress and of friction parameters. And then you compare the synthetics of all these forward simulation with observed data, and you look for the models that minimize the misfits between the observation and the synthetic data.
And
so, yeah, sorry.
And from that you get your error, right?
Yeah, so you have several million of forward simulations, and because the data are at the surface and the fault is at depth, so it's not very well constrained. So there is a lot of models that explain equally well the data, and so you have a large number of models that explain equally well the data, and so from this you can compute mean models, and you can compute, I don't know, the standard deviation or something like that. But so I have never done this myself, but it's the idea.
Yeah. And for your Turkey example, how did you compute your error there?
The Turkey example is it's not an inversion. We just prescribe some initial condition and we run the simulation. We did a few trial and errors just to find the input parameters that best explain the data. So we haven't run several millions of forward simulation for Turkey. Just like, well, it's still a lot, but not millions. And then we look at some, we change a little bit the parameter until we found a model we are satisfied with, let's say.
Yeah, but
So
how
we
do
don't
you...
estimate uncertainties for.
Yeah, okay,
Yeah.
yeah. And
We
also
don't.
for your second rupture, if you go to the slide with your pre-stresses, with the R values.
Yes. For these models,
No, I mean for the second Turkey rupture, I mean.
Yeah, okay, so Turkey, sorry. This one, maybe, the R value?
Yeah, right. But not this one. I think it was 29 or something.
29. Here. Oh, yeah. Okay.
Yeah, where you computed like the R values in figure H.
Yeah.
It looks
How?
like a...
Oh, yeah, because it's weird right here on the East Anatolian fault. That is what you mean?
Yeah, and also where the rupture did not propagate, there's
So
a low R value, but it looks kind of similarly oriented to the red part where the rupture actually nucleated.
yeah. Okay, so there is two things. So this, sorry, I didn't say it earlier. So this R value distribution is computed after the end of the first event. So that's why it's very low on the East Anatolian fault here, because the first event already ruptured. So the pre-stress level is very low on these parts. Yeah, and then on this segment here, the pre-stress is very low because the stress regime we assume is is not well oriented to maximize the pre-stress level on this fault. Does it answer your question?
Yeah, but you keep those homogeneous, right? The whole stress regime for...
No, not entirely. It's not completely homogeneous. I'm looking for the slide. It's here. So we have some data, some observationally constrained from Guverkin and collaborator about how SHMX varies in the area. So we use this information to prescribe the orientation of the stress field along the fault system. So it doesn't perfectly match the data. In some area, we rotate a little bit SHMX so it can reproduce the rupture characteristic that we observed.
Yeah, but that's cool. Yeah, thank you.
Yeah, Mathilde, this orientation that you're showing are based from what type of measurements?
Stress tensor invariant. So,
Okay, so focal mechanisms?
Yeah.
Okay. Any questions, anybody? Or maybe I can ask, all right, yeah, Mikey has one. So Mikey, go ahead.
Yes, you said that you concluded that the first Turkey earthquake didn't trigger the second earthquake, and did you just mean dynamically trigger, or do you think it can be triggered by, for example, viscoelastic stress transfer or pore pressure changes that have a time delay?
Yeah, of course. Of course, right. So I said that because, I said co-seismically during the rupture, the second event, the first event didn't trigger the second one. And if we look just as the static column stress change produced by the first event on the second fault, then the stress change are not very high, and in particular at the epicenter. The stress change at the epicenter produced by the first event on the fault of the second event is very low. But yes, we haven't explored complex processes. I mean, with SISOL, with dynamic rupture simulation, we can only model the co-seismic phase, and so every transitory processes are not taken into account. And I guess, yes, I mean, the both earthquakes are 9 hours apart. I guess there is some processes that induce that.
I mean, viscoelasticity is not at a good scale for this. I mean, you can
it's a
expect
more
viscoelastic
fluid pressure.
processes. Yeah, fluid pressure could possibly, but
yes.
So yeah, I was thinking still about the Turkish doublet. So you mentioned that, as Daniel also mentioned, that the part of the fault that would join the two faults didn't break, and
yes.
It went to the northeast. So you said that it's because the pre-stress level wasn't high enough, but then I mean it's something that you control. Is that right? The pre-stress level. The orientation I understand is based on inversions, but I mean the pre-stress itself, I mean the absolute value.
So the absolute value, we don't control it directly. We don't say, okay, the shear stress is this high on the faults. We use, so I haven't explained it, I think, or maybe for the other study, we use the pre-stress level R, which is, we use this parameter to prescribe the amplitude of the stress in the stress tensor. So it's a feature of Sisal when we want to use an Anderson stress regime for our simulation to prescribe the amplitude of stress. So the amplitude of the stress are controlled by the air ratio and by the lithostatic stress. So it's like kind of proportional to rho GZ. So we have the stress orientation with SHMAX. We have the relative amplitude between the three principal stress components using the stress shape ratio. And we set this parameter R, which tells you how close you want to be from the rupture. And it uses the Coulomb theory to compute
but I mean,
that.
this or not is something that you prescribe. I mean, there's no way you can.
R is something that we prescribe.
Yeah.
Of course, but we how to say that? So we prescribe a quiet, rather homogeneous air ratio in the medium, and this homogeneous air ratio and is translated as heterogeneous on the modeled fault system, because our faults that we model are not necessarily super well oriented within the stress regime that we assume. And yeah. And so with the parameters that reproduce super well both earthquake, it ends up that it lead to a very low pre-stress level on this small segment.
Okay.
So we were like surprised and happy about that. It's quite cool. No, it wasn't on purpose.
So yeah, I have maybe a second question, and then we'll see if somebody else has ideas. But hold on. So yeah, I was wondering about the arrest. So you saying, I mean, so the fault length is something that you input, so you cannot predict how large the earthquake will be. So you assume that it will arrest where it arrested. Is that right?
Yes. Yes. Okay. It's right. Yeah.
So is there something there, I mean, that you can exploit in order to say maybe, the pre-stress level or, whatever parameter, should be set to this value, because otherwise, the rupture would not stop there. Is that
yes.
Yeah.
So you were talking about still about this segment here?
No, even
generally
the
speaking.
main rupture itself, or rupture, so if you don't impose, the end of the fault, then, it possibly could, go on.
Yes, exactly. Yes. Usually when there is something wrong with the length of the fault, there is some the rupture front that is back how do we say that? The rupture front goes back in the other direction. So we know that there is something wrong with the initial condition in that case. Yeah. So we.
But that's not something that you can find that you've tried to use, in order to better constrain the parameters.
No.
Okay, it's just imposed and that's it. Yeah.
Yeah.
Okay.
Yeah.
All right. So any other questions for Mathilde? Anybody? Okay. So maybe we can stop. Thanks a lot, Mathilde, for your presentation again.
You're welcome.
Very nice.
Thank you.
That's quite different from what you did during the PhD.
Yes. yes. But I'm still doing theodicy as well.
Yeah. Okay.
I like both worlds.
All right. Nice. Very different. Okay, so guys, we won't see each other until September. So I hope everybody will work well and then rest well as well in the meantime. Enjoy the summer break. And I hope to see you all in good, spirit in September then. Okay, so bye-bye, everybody.
Bye.
Thanks a lot.
Thank you.
Thanks,
Bye-bye.
Mathilde.
Thank
Thank
you.
Bye-bye.
Thanks, everybody. Ciao.
Bye.
Bye,
Thank you.
everyone.
Bye.
Thanks a lot.